Okay, so data breakdown November 2018 into the questions and the expected answers. So let's go through this as quickly as possible. So that was the first question. We looked at it in the previous videos. So name the species that would be your isotopes. What is relative atomic mass? That would be the mass of an element compared to 1/12 the mass of carbon-12 atoms. Then calculate relative atomic mass of bromine. So if you're given isotopes with their relative abundances and also their M&D ratios, what you have to do is simply multiply the abundance and the given mass for each and every isotope that is present. So we have an abundance of 50.52 out of 100 for the isotope of bromine 79, and if we take away 50.52 from 100, we have 49.48 for the isotope of bromine 81. So 49.48 out of 100 times 81. You add these successively. Chirokapuama isotopes akawanda, say you do the same and you add. So in this case, we have a total of 79.99. Let's move on. Define bond energy. That should be very simple for you. The amount of energy required to break one more of covalent bonds in a molecule. Please go and like, subscribe, and share this video with someone. It takes a lot of effort to create these videos, so do us a simple favor, go and like our YouTube channel. Also share this video with someone so that we continue to make more of these videos. Okay, and Mberi Tirikuti Shushu methane reacts with chlorine according to this equation. So calculate the enthalpy change for the reaction. So for you to be able to do that, you need to appreciate the amount of energy that was required to break the bonds to your left inside in methane and also in chlorine, and you compare that with the energy that was created or released when you made your chloromethane and hydrogen chloride. So you just add those two energies. For the energy changes to your left, it's going to be positive. The energy changes to your right are all going to be negative. So you put those together and you get the total energy change for that reaction. Okay, so that is the calculation, but take note there's an error here. Here we didn't make a chlorine to chlorine bond, rather we made a carbon to chlorine bond. So that's an error. You can check that one out. Okay, so you have a total there of 1220. Let's see if we can move on. Write an equation that represents the second ionization energy of oxygen. So take note here, we are seeing second, so the first electron is already gone, and I want to move to this O2 plus. Okay, so I want to move to O2 plus. So you should avoid the error of starting with the neutral oxygen atom in this case. So that's the answer. Okay, let's start and explain any two factors that affect ionization energy of an element. The amount of energy that is required to remove one more of electrons. So you know it depends on the distance from the nucleus to the outer electrons, the charge on the nucleus, shielding effect. Those are the factors, but you need to explain how they affect. So for atomic radius, the further away from the nucleus, the less attraction by the positive nucleus, and hence less ionization energy is required. And then when there's greater shielding, the outer electrons are shielded by inner electrons from the attractive force of the nucleus. Hence, a small amount of ionization energy is going to be required in that case when you have a greater shielding effect. The higher the nuclear charge, the higher the attraction of the between the nucleus and the outer shell electrons, and hence there's an error again here in our marking scheme. Hence, a large amount of energy is required if you have a greater nuclear charge. So take note of that. State two factors that affect the magnitude of lattice enthalpy. This would be the amount of energy that is required to form your solid lattice structure in ionic compounds. So what are the factors that affect the amount of energy that is released when you form that solid lattice structure? It depends on the charge of the ion, the radius of the ion. That makes sense. Okay, explain how the factors that you have stated in B1 affect the magnitude of the lattice enthalpy. So let's see here if it makes sense. The greater the charge, the stronger the attractive force, and the higher the lattice enthalpy energy produced. That's correct. The smaller the radius, the stronger the force of attraction, is the higher the lattice energy. Yes, that makes a lot of sense. All right, so those are the two factors and the explanations given there. Explain how lattice enthalpy affects the solubility of ionic compounds. So you should remember that when you are dissolving these solid ionic compounds, you're actually breaking the lattice energy. So the lattice energy becomes lattice dissociation energy, which will be endothermic in the case. It was exothermic when you were forming the lattice, but it becomes endothermic as you break the lattice. Then there's another energy which is now going to be exothermic, which is the hydration enthalpy. So you need to check this equation. Solubility here, the enthalpy change of solution is going to be dependent on your negative lattice, which is the lattice dissociation enthalpy, plus the hydration. So negative lattice there, that would be your endothermic lattice dissociation enthalpy. Okay, that being said, how does that affect the solubility? So the explanation here is, if lattice energy is higher than hydration enthalpy, the compound does not dissolve. If lattice energy is lower than hydration energy, then the compound will dissolve. That makes a lot of sense. So in other words, we can expand this and say that if the lattice energy is higher than the hydration enthalpy, that would be the amount of energy required to break the bonds, the lattice, if it's higher than the amount of energy released when the lattice has been destroyed and the ions are associating with water molecules. If those energies, if the endothermic energy here is larger, then the compound is not going to break, it's not going to dissolve. If it's larger than the energy that is released, and the reverse is true. Let's try to move on as quickly as possible. Write an equation of the decomposition of magnesium carbonate. State any one use of the products formed in the reaction above. So let's look at the equation. The carbonates are going to decompose into the metal oxides and carbon dioxide gas. This is important for you to remember for these group 2 carbonates. Magnesium oxide can be used as lining in furnaces, and carbon dioxide can be used in fire extinguishers. Okay, what else is here? Describe and explain the trend in the decomposition of group 2 carbonates. What is the trend? The thermal decomposition decreases down the group. The cation ionic size increases, decreasing the polarizing power of the cation, and hence the compound becomes more stable or more difficult to break. That makes a lot of sense. So we're going to make this video shorter. I'm going to end here. Write the chemical equations to show how sulfuric acid reacts with potassium bromide and sodium chloride. So let's see here. It's about sulfuric acid as an oxidizing agent for those the bromide ions and the chloride ions in that case. So how does it react in this case? That makes a lot of sense. We're going to have bromine being formed, and for chlorine there we are going to end with hydrogen chloride. Okay, any observations? We have white fumes in the first case and red-brown fumes, and we have white fumes in the second case. So we're going to scrutinize this question further in our next video. I need to make the videos shorter so that we can be able to share them on WhatsApp. So I'll meet you in the next video as we continue to scrutinize this paper. See you in the next video. Okay, so let's continue with our scrutiny of November 2018 chemistry, advanced level Zimsec. We ended with this question in the previous video. where we saw that sulfuric acid here is acting as an oxidizing agent to those bromide or chloride ions. So it's important to take note here that for the bromide here, we were able to oxidize further to bromine gas, but here we ended here. So it means that this one, the chloride, are more difficult to oxidize using sulfuric acid, and these ones are easier. So this should tally with what we see on the periodic table. It should be that bromine is lower than chlorine. You can check that with your periodic table. Why? Because as the atoms get larger as you go down the group, the electrons are further and further away from the nucleus, and hence, remember those factors shielding atomic radius, there's a less attractive force between the nucleus and the outer shell electrons, and hence they are easier to remove, easier to oxidize. So bromine should be lower than chlorine. Go check that one out. Let's move on. We saw the observations there that you're going to see white fumes and red-brown fumes for the bromine. Then here, let's see, what do we have? Outline how polypropylamine can be prepared from chloroethane. So you're starting with a halogen alkane there, and you want to turn it into an amine. So let's look at the suggested answer. So what you have to do first, potassium cyanide, ethanolic, and then you increase your carbon chain there. You now have your nitrile group, and you reduce the nitrile group to an amine group. Makes a lot of sense. So that's correct. Very correct, this one. Okay. Compare the basicity of propylamine with that of phenylamine. So you have an aliphatic amine there versus another one that contains the benzene ring here. So what's going to happen here? Propylamine is more basic than phenylamine. Why? Because the benzene ring is going to withdraw electrons from the nitrogen. So what does this mean? When the benzene ring is going to withdraw electrons from our nitrogen, these electrons become less available, so they are drawn towards this ring. They are less available to bond with this H+. So it's going to be weak in terms of attracting our protons, hence it becomes a weak base. So that is the point there, that the other one, which is a straight chained amine, the electrons, the propyl group is going to push the electrons. The propyl is going to be you're going to have 3 carbons prop, all right, and this is going to push electrons towards the nitrogen group. Okay, let me show the actual propyl group here. So this would be your propyl group. So this one is going to push electrons towards the nitrogen, making that lone pair of electrons more available, or increasing the electron density around the nitrogen atom, making it more attractive to the H+ ions. So it's going to be more basic in that sense. Okay, let's move on. What else is here? What else is here? So write an equation to show how propylamine dissolves in water. So since it's basic, it's going to accept a proton. So that's shown there. Yeah, we've accepted a proton there. Okay, let's move on. State the acid-base nature of the solution formed. So the solution formed here is going to be basic. It's going to be basic. The solution formed is going to be basic because here you now have these OH ions, so you're going to have a basic solution. Okay, so let's move on. Okay, let's move on to the next question. Superglue contains an organic compound A shown there. Name any one functional group. I see a lot of functional groups here. I see this group, I see this group. Okay, rather it's an ester link here. Okay, so let's see in the suggested answers there. You have an ester, an alkene, and a nitrile. So we just wanted one. Okay, what else is here? State the type of polymerization that compound A can undergo. You have an alkene group there, so addition polymerization. Draw the repeat unit. So in the repeat unit here, it's important here that you condense this. So you see that structure there. Let's go back to our compound. Okay, there it is. So it's important that you condense this part here, and you also show this bond is going to open. So these hydrogens are going to be here, and you open this bond here, and you condense this. Rather you just put a CN here, and you condense this. You open this bond. So this is what we should expect in our answers. So there it is. Okay, it's important to show the open bonds, and also this should be vertical like that. Okay, all right, so no angles when you're showing that repeat unit. If you're in Concession Pindura or any places around Glendale, let's meet in Glendale so that we can do it further than what you're doing here. We can do an even deeper analysis of these papers with all the relevant theory explained to you. So tell a friend to tell a friend. You can join our WhatsApp groups for further information. Okay, let's continue. Please share this video to someone who might find this helpful. So the structural formula of jasmine is shown in Fig 5.1. So what you're supposed to do first is identify the functional groups. No matter how novel the chemical looks to you, identify the functional groups. Whatever functional groups you can identify, locate them, nail them down, and be sure that I have these functional groups. Okay, so I have identified my 3 functional groups there. Okay, so draw the structural formula of the organic product formed when jasmine reacts with let's see here. Firstly, with 2.4-dinitrophenyl hydrazine. So this one is a popular reagent, and I also urge you to create a table such as this one, where you say popular reagent, you say target functional group, and you put conditions here. Because we have our popular reagents, and write it like that, popular reagent. We have our popular reagents in organic chemistry such as 2.4-dinitrophenyl, your potassium permanganate, your potassium dichromate, your lithium tetrahydroborate, your sulfuric acid, sodium hydroxide, all such popular reagents. Try to list them here. There are not so many. And try to list the target functional groups. Every time you see your lithium tetrahydroaluminate, for example, what are the associated functional groups? So list them and try to list the conditions under which it reacts. You can even add this table and say organic product. Organic product. Okay, so try to do that table. It takes some effort, but it's going to be very, very helpful. You'll be able to map out all the popular reagents and the products that they form. Okay, so 2.4, that reacts with your aldehydes and ketones, and so it's used to test for aldehydes or ketones. So it's supposed to attach where there is an aldehyde or ketone group. This is a ketone group because you have an R group there, so that's a ketone. The rest of the molecule is going to be passive, it's not going to participate in that reaction. That's very important. So let's see in our suggested answers. So there you have it. You should also know how you attach this 2.4-dinitrophenol hydrogen to this ketone group. It's important. You can go back and check with your theory or join our WhatsApp group so that we can discuss this further. Okay, so there you have it. Let's move on to the next reagent, which is in this case our lithium tetrahydroaluminate, which is a popular and powerful reducing agent. So what is it going to do? If you remember a theory, if you start off with alcohols, you can oxidize them to aldehydes and ketones, depending of course on whether it's a primary, secondary, or tertiary alcohol. You can also join us so that we discuss this further. So you can oxidize alcohols all the way to ketones. But if you wanted to do the reverse, then what you have to do is reduce. So you need powerful reducing agents such as this one. So it's going to reduce let's go back. So here, this can be reduced back to the alcohol group. So let's see. In the suggested answers, you can see this is now an alcohol group. This remains passive. So it's like the lock and key hypothesis when it comes to organic chemistry. Specific reagents are going to target specific functional groups under specific conditions. Okay, let's move on. Another reagent called dilute potassium manganate. This one is a popular and powerful oxidizing agent. So it's going to oxidize alkenes. All the alkenes group are going to be targeted. Alkenes, or if you have this group here with a triple bond, these can all be oxidized. So what do you have? So you see oxidation has taken place. The alkene group is no longer here. The alkene group is no longer here. We have our OH group, so it can oxidize those alkenes to diols or alcohols. So that is what has happened there. There has been oxidation. It has targeted the alkene groups. And as before, this one remains intact, our ketone group. So specific functional groups under specific conditions. Then what other reagent we have? We have our hot concentrated potassium manganate. So this one, when it's hot and concentrated, it's going to split your alkene groups and oxidize the groups. So there's been oxidation there, but most importantly, there's been a split of that group. There's been a split of that group. And you see this group has also been split and oxidized. It has been detached from this carbon. And there's also oxidation that has taken place there. So that's very important. It's clearly outlined in our theory what potassium permanganate does to alkene groups. So you can join us for further discussions. Let's see if we can put an end to this paper studying the two uses of chlorofluorocarbons. With the aid of equations, explain the detrimental effects of chlorofluorocarbons to the environment. So CFCs can be used here in refrigerators, air conditioning units, solvents in aerosol sprays. And the detrimental environmental effect is that it destroys the ozone layer. I don't see the ozone as part of these equations. So I think that's an error there. Okay, let's move on. We have this process that's shown there. Shows the apparatus used to separate a mixture of ortho-nitrophenol and para-nitrophenol. So the ortho and para, basically, when it's ortho, they are going to be the OH and the nitro group are going to be next to each other like that, adjacent carbons, and then for the para, it's going to be, they're going to be opposite like that. So what does this tell you about the properties of the molecule? Well, there is the issue of hydrogen bonding. In one case, there's going to be intra molecular hydrogen bonding. In the other, there's going to be intermolecular hydrogen bonding. Okay, so let's see what we have here. Name the separating technique shown. So the technique there would be steam distillation. You can see the steam there getting in there. If you need further explanation as to how this works, you can always contact me, join our WhatsApp groups or our paid groups. State with reasons the composition of the distillate. So it's going to be ortho-nitrophenol and water mixture. Like I said before, there's intramolecular hydrogen bonding in the ortho-nitrophenol, which reduces its solubility in water, increases its volatility, so it's the one that's going to vaporize and be collected there. Then there's intermolecular hydrogen bonding in the para-nitrophenol, which increases molecular weight, reduces solubility. So there's going to be that ortho-nitrophenol in that distillate. Okay, what else is here? Explain the formation of landfills, the formation in landfills of leachate and methane. So leachate, what is leachate? The black liquid formed by water, which percolates through decomposing organic matter, collecting partly decomposing material and ions. So that's your leachate, which drips underground. Methane comes from your anaerobic decomposition of organic material, and the equation is shown there. That's correct. So what else do we have? One problem caused by leachate. So the leachate, you saw that it collects part of partly decomposing material and ions. So there's risk of what? Underground water pollution. So basically, this is what I had for you in this paper. If there are still some gray areas, let's meet in Glendale. If you are around the Glendale area, the Four Keys College will be at Umuzi Farm. You can contact me so that we can do online lessons and do further scrutiny of these concepts so that you have a clear grasp and understanding of your A-level chemistry. So I'll see you in the next video.